Hi dear friends, good morning. This is Bhusar Sonone, Assistant Professor, Department of Chemistry, Gokul Education Societies, Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the last part of the video of this lecture series, we have studied about the second order reaction. We also tried to discuss the equation for the kinetics of second order reaction, and finally we derive equation for the rate constant of second order reaction as K2 is equal to 1 upon A into T into x upon A minus x. Dear friends, based upon the same second order reaction, today in this part of the video we are going to discuss, we are going to study about the characteristics of second order reaction. If we will look at the rate constant of second order reaction, then definitely we all are well known about the equation for the rate constant of second order reaction as K2 is equal to 1 upon A into T into x upon A minus x. In this equation, definitely you are well known about the x, A minus x. These are all the concentration. So x upon A minus x is the concentration. So this is the ratio of concentration that will cancel, and hence whenever we will talk about the first characteristic of the second order reaction, then you will come to that this rate constant of second order reaction will found to contain the one concentration term in the denominator than numerator. So the unit of this rate constant of the rate constant of second order rate constant will be reciprocal of concentration and the reciprocal of time, and that's why the unit will be mole per dm cube and it's reciprocal. So this unit will be, and the per time means dm cube per mole per second. Such type of the numeric MCQ can be asked to you in the examination. So this is the now the second characteristic of the second order reaction is the time required to complete the definite fraction of the reaction or the half-life period of the second order reaction. Here, dear friends, we all are aware about the important characteristic of reaction is that the fact time taken to complete the fraction of the reaction is inversely proportional to the initial concentration of the reaction. So half-life period is inversely proportional to the initial concentration small a, and that can be shown here. Suppose T1 half is the half-life period of the reaction, and at the half-life period definitely the value of concentration of product will be half of the initial concentration, means the x is equal to a by 2, and this is the equation for the second order rate constant 1 upon a into t, but here this equation can be written for the time. So time is equal to 1 upon k into a into x upon a minus x, and if then in this equation we will put t1 by 2 instead of t and a by 2 instead of x, then we will get the equation as, so here whenever we will put x is equal to a by 2 and t is equal to t1 by 2, then definitely we will get this equation. So this a by 2 divided by a minus a by 2, that will also remain the a by 2. So this term, whole term will get cancelled, and simply the half-life period of second order reaction will be equal to only 1 upon k into a. This k is the rate constant and a is the initial concentration, so this k is constant. Therefore from this equation we can say that the half-life period of second order reaction is always inversely proportional to the initial concentration of the reactant. This is very simple. The half-life period of second order reaction is inversely proportional to the initial concentration of the reactant, and definitely this can be applicable to the completion of any definite fraction of the reaction also. Next characteristic, whenever we will plot the graph of this second order reaction, then definitely it shows the particular nature of the graph that can be predicted from here. So in the graphical interpretation, suppose for the equal initial concentration of the second order reaction, we got this equation k is equal to 1 upon a into t into x upon a minus x, and this is the equation for the rate constant of second order reaction. If we will rearrange this equation, then I will transfer this t on this side, and this kt is equal to 1 upon a minus x minus 1 upon a, because after solving whole this bracket, definitely you will again get this. So that's why these both the terms are exactly identical, only we have rearranged this equation. And after simplification, I will write this equation for 1 upon a minus x is equal to k into t into plus 1 upon a. This can be transferred to this side, so that will become 1 upon a plus 1 upon a. And this equation, it is the equation of straight line y is equal to mx plus c. If this equation is compared with the equation of straight line y is equal to mx plus c, so this equation is having the slope of this line will be m equal to k, and the y-intercept will be 1 upon a. And that's why whenever we will plot the graph of 1 upon a minus x versus time, then it will give a straight line having slope is equal to k, and the y-intercept will be equal to 1 upon a. And that's why the plot of 1 upon a minus x versus time will give a straight line having positive slope equal to k, and the y-intercept will be equal to 1 upon a. So this is the straight line that we are getting, and the slope of this line will be equal to k, and y-intercept will be equal to 1 upon a. So from this slope we can, from this graph we can calculate the slope of the line and the y-intercept 1 upon a, and definitely from this we are also able to calculate the initial concentration of the reactant also. So this is the nature of graph generally that we are getting for the second order kinetics. Based upon the second order reaction, again we can discuss some numericals here. The second order reaction with equal initial concentration of the reactant is 75% completed in 1 hour. Then calculate the how much will be left unreacted at the end of 2 hours. So here 75% of the reaction is completed in 1 hour, then how much will be left unreacted after 2 hours? So if 75% reacted in 1 hour, then how much reactant left unreacted after 1 hour, that to be calculated here. So what things are given here and what things to be calculated, that is necessary to understand. This is the condition for the initial concentration, and for this we have the equation for rate constant k is equal to 1 upon a into t into x upon a minus x. So already given as the reaction is 75% completed, means the amount of product formed x will be 75% compared to 100, and whenever it is compared to 1 it will be fraction, so the 0.75 of initial concentration. And a minus x concentration, that is amount of left unreacted, that will be 0.25 out of 1. Okay, only in the numerical it is given in the percentage, and in this during the to solve this numerical we have written in the fraction. So if we put x is equal to 0.75 a and a minus x is equal to 0.25 of a, then definitely we will get this equation. So this a and this a will get cancelled, and after solving all this, definitely we will get this 3 upon a, k is equal to 3 upon a. And if we put this k is equal to 3 upon a in the second case, so what will be the value of x after 2 hours? So time will be 2. Again with this equation, a will remain as it is, x upon a minus x, and the k is equal to 1 3 by a. So this a and this a will get cancelled, okay, and only 3. So this that is 2 into 3, that will become 6, and that will be equal to x upon a minus x. If this 6 into a minus x is multiplied, then definitely we will be able to 6a minus 6x is equal to x. So that will become, that is 6a minus 6x. Okay, if minus 6x is transferred to this side, then it will be equal to 6a is equal to x plus 6x. So that will become 7x. So x is equal to 6 upon 7. I hope you can understand. 6a is equal to 7x. Therefore, what we can write, 6a is equal to 7x. Therefore, x is equal to 6 upon 7 into a, and that will be equal to 0.857 of a. So amount of left unreacted at the end of 2 hours will be a minus x. So this is the value of what, x, and that will be 1 minus 0.857. If a is equal to 1, then that will be equal to 0.143. That will be equal to, in percentage, 14.3% will be left unreacted. So dear friends, in this part of the video we try to understand some characteristics of second order reaction as well as some numericals based upon the second order reaction. So this is another numerical that can be also discussed discuss here. So second order reaction with equal initial concentration is 20% completed in 50 minutes, and calculate the time taken for the 40% of the completion of the reaction. So here, if 20% completed in 50 minutes, then how much time is required for the completion of 40%? Definitely one can think about the cross multiplication, but this is not the correct method to solve this. If a is equal to 100%, then x is equal to 20% completed in 50 minutes. So therefore a minus x will be, if a is equal to 100, x is equal to 20, then a minus x will be 80. If you will put all these values in the equation for the this 1 up k is equal to 1 upon a into t into x upon a minus x, definitely this a is equal to 100 into t 50, a, the x upon a minus x is equal to 20, a minus x will be definitely 80, and after solving all this we will get the value of k 5 into 10 raised to minus 5 per minute. Okay, and this, in the second case, what things are given, that is 1 upon, this time is to be calculated here. So we have written this equation for the time t, 1 upon a into k into x upon a minus x. Here that is k is already calculated here, 5 into 10 raised to minus 5. A is given 100, this is the k, and that is time is to be calculated for 40% of the completion, means a is equal to 100, x is equal to 40, so definitely a minus x will be 60. And after making the simplification of all these calculations, definitely time will be equal to 133.33 minutes. So this is again the another numerical based upon the second order reaction. So dear friends, in this part of the video we try to understand the various characteristics of second order reaction and some numericals based upon the second order reaction. So in the next part of the video we will try to discuss about the speed order reaction and some methods for the determination of order of reaction that we will discuss in the next part of the video. Thank you very much.